I hope you're all keeping safe. I welcome you to today's lecture. We'll be covering fatigue today, high cycle fatigue, low cycle fatigue, and then next week I'll be going into fracture.
So the topic of fatigue is one that requires tremendous amount of consideration. And the reason for that is because a lot of structures, especially some aircraft structures, will be subject to cyclic loading. So what is fatigue? If we use the ASTM definition, is a process of progressive localized permanent structural change occurring in a material subjected to the conditions and which produce fluctuating stresses and strains at some points, and which may culminate in crack or complete fracture after a sufficient number of fluctuations. So it is important to understand that it's unlikely you will have fatigue if the structure is only exposed to a single cycle. This issue of fatigue really comes into play when you have multiple cycles being applied to a particular structure. Another point I want to consider here is that if you have taken a little aluminum wire, like a clip, and you have bent that clip back and forth, you will see that if you apply very little fluctuation, it's unlikely you will break the clip. But if you apply a significant amount of fluctuation and you plastically deform the clip, it will take very few cycles to break the clip. And so, as you can see there, the amplitude matters, and also the number of cycles. If you cycle something for a long time, it's more likely to fail than if you were to cycle it very few times. And so, if I were to translate what the ASTM is telling us, is that fatigue is basically cyclic damage leading to local cracking or fracture. And the process for fatigue failure is crack initiation, crack nucleation, and we call this the initiation aspect. And then we can go, that crack will go now under a micro crack growth. And from micro, it turns into macro, and then it turns into failure. On the right-hand side, and I'll be covering this picture quite a bit, the initiation will occur at a particular point on the surface and then emanate from that surface, from that point, outwards. And I'll go into more details about some of the phases of fracture. So the evolution of fatigue requirements has evolved. Historically, before the 1950s, the design requirements were driven by basic engineering properties. And the material properties were really driven by strength and creep. From the 60s to 70s, there's more emphasis for designing against fatigue and considering the high cycle fatigue and low cycle fatigue. I'll be covering some of that history, which really predates this time. It goes even back to the late 1800s. In the late 1970s, damage tolerance requirements were looked at, and the material properties for that were crack growth. This last row we'll be covering next week. But it's important to understand that fatigue and fracture, while somewhat related, are different design drivers. For example, for fatigue, what I'm looking for is that initiation. Once the crack initiates, perhaps I can then switch into damage tolerance. But when I look at damage tolerance, I am assuming that there's some inherent defect that needs to be considered in the design. And if there's no initial defect, then perhaps the fatigue initiation from high cycle or low cycle is the initial flaw, causes the initial flaw, then we then analyze the damage tolerance. So what are the loadings that can produce stresses that are variable, repeated, alternating, or fluctuating? There could be a lot of different sources, such as vibration, statically applying loading, for example, an aircraft that takes off and lands will see a ground to air cycle. And you can see there that the fuselage will get pressurized and then depressurized when the aircraft lands. Um, Failure there occurs after many stress cycles. Failure is by sudden ultimate fracture. There's no visible warning in advance of the failure, and it can take many forms, like fatigue at notches. We see these kind of fatigue failures in rolling contact fatigue. So if you have a ball bearing, you could have either fracture of the bearing or the cage that holds the bearing. We have fretting fatigue, corrosion fatigue, and creep fatigue. Notches are great candidates for fatigue initiation. And notches are very difficult to avoid in many structures and machines, and notch effects have always been a key problem in the study of fatigue. And the idea is really to decrease the stress concentration as much as you can, especially if the structure is subjected to the fatigue environments. Thread roots and transition between the head and the shank can be a problem. Rivet holes in sheets, welds on plates, keyways on shafts. Those are just few examples. So what are the factors that influence fatigue damage? You have the stress range, and I discussed that before. If I have a small amount of stress range, such as you have to take an aluminum clip and you hardly bend it back and forth, you're unlikely to fatigue that part. But if I now take that clip and aluminum wire and I bend it very dramatically back and forth, then you're more likely to influence the fatigue damage and expedite the process. So stress range is really the basic cause of plastic deformation, and consequently, it is the one that can cause the accumulation of damage. Another point I want to make is the mean stress. If you have a mean stress that exists in a part, you're also likely to influence fatigue damage. Stress gradients, for example, I'll show you later that bending is a more favorable loading mode than an axial loading, because when you have bending, fatigue crack, when you have bending on a part, if there's a bending of a part, fatigue cracks will propagate into a lower region of lower stresses. And so it is proven, and I'll show you some data, that bending is actually more benign if I were to axially load the sample cyclically. Tensile and yield strength, higher strength materials will resist plastic deformation, and hence, and especially if you have higher yield. So if you have a better yield performance, higher fatigue strength occurs. And so you have longer lives. Most ductile materials will perform better at shorter lives. The quality of the material is important. So if you have metallurgic defects such as inclusion seams, internal tears, those could be points of initiation for fatigue. Temperature usually also changes the yield strength, and as a consequence, it will impact the fatigue resistance. That's an important consideration in these applications. Another point I want to make sure is understood is that these are not the only things. You have frequency, if you have a high rate of straining, so at high frequencies, the metal component could become self-heated, and then that could be a feedback loop back into the temperature increasing, which then could decrease the local properties as well. I also want to point out that the loading cycle sequence can matter sometimes. So potential crack causes could be inherent to the material, such as imperfections in castings, precipitates in aluminum 6061 as an example, coalescing of internal dislocations, or you may have grain boundary issues. You could have fabrication-related issues, such as tooling marks, improper assembly, thermally induced well cracks, such as areas that have been affected by the heat. Um, you have use-related stuff like high-stress areas. You can have scratches or unintended use um, being a problem. So for crack initiation, high cycle fatigue and low cycle fatigue are treated separately. And the question is why? The general distinction is that usually high cycle fatigue, you're looking at failing in the millions of cycles. And the failure criteria is typically based on a allowable stress. In some applications, strains can also be used as long as you have the data to support it. High cycle fatigue usually occurs when you have low amplitude loading and you're not going into the yield regime, but you have there's high frequency in this component, and the loading is actually high frequency. An example of that could be due to resonant vibration most of the time. Low cycle fatigue occurs usually when you have high plastic deformation. And in those scenarios, when you have low cycle fatigue, you better have an accurate life prediction, because now you're looking at low cycle fatigue and you're only talking about thousands of cycles. Here's an example of a fatigue crack growth of a Southwest airline. And there's cracking there at the roof of the Southwest airline, cracking that's going through multiple points in an overlapping skin of the design. And the point I want to make here is that this scenario of fatigue cracking of a Southwest airline was not really expected. This has happened multiple times now. I think it's important to understand that the way this particular airline operates is that they have a quick turnarounds, and they have very short flights, and they predicate themselves into even flying each Southwest Airlines more than 3 or 4 times a day. Some of them can reach 6, 7 times, and that is not common in the airline industry. But their model is such that you are taking off quite a bit and landing. And so you may not be able to use hours in service as a good metric for inspections because of that. And as a consequence, this particular situation had to be revisited, because clearly fatigue from a hole was a particular concern, and it was driven really by the ground to takeoff and ground to air cycles, back to ground. That's one cycle. That's one complete cycle. Fatigue cracking in other aircraft applications is hard to see here, but there's a crack near a hole. We also seen fatigue issues with turbo machinery in engines, for example, and you have severe structural issues and challenges that you're going to see, especially with engine applications. High structural loads, fatigue creep, and you definitely need something that's environmentally friendly, fatigue cracking resistant, that's able to resist initiation and propagation, creep resistant, strong, lightweight. That you want something that's predictable, affordable, and environmentally stable. Nickel superalloys tend to do a good job of those. Combustion turbine components present a severe thermal fatigue cracking challenge. You have mechanical fatigue caused by cyclic thermal strains, high temperatures accelerating fatigue damage, and then you have oxidation at the crack tip that can make things worse. Here's an example from the literature of a fatigue of a major challenge in a turbo machinery. Here you have a rotor that has exhibited fatigue crack initiation. It's caused, in this case, is clearly caused by load cycle fatigue. And load cyclic loading, it occurs at cyclic loads well below the ultimate strength. And that's the issue. You may think that you have sufficient strength margin against the ultimate capability, but it's really the load cycling that's causing this damage. High cycle fatigue in a turbo machinery will be caused by vibration, the rotation of the rotor, and the crossings against the engine order modes. Now in your homework, you're gonna have a homework on this, and I'm gonna ask you to really look at the conditions for fatigue for an engine, and I'm going to have you look at something called the Campbell diagram, which is really a resonant diagram where you're taking the natural frequencies of the rotor, and then you are basically comparing those natural frequencies to the operating engine forcing frequencies. And so I'll put a link below this video so you can go ahead and start looking at that video for what you need to do in your homework. Low cycle fatigue will be caused typically by the engine cyclic behavior. So that means starts, shut down, and the transients that go along with that. We have the famous Aloha Airlines Flight 243. The failure had occurred due to cyclic loading. The mid-flight fuselage failure was caused by corrosion-assisted fatigue in that example. All machine and structural designs are problems in fatigue because we have the forces of nature that are in play. Here's an example of a circular spall that began at a large subsurface inclusion in a hardened steel roll. And hopefully you'll be an expert very soon of telling me where you think fatigue initiated. We have here an example of a lug, and at that lug, the crack initiated. Now, I want to point out, you could try to have a great fillet radii, but sometimes you could have design features that were not intended. In this case, a machining operation caused this particular sharp corner. While your drawing requirements were one, the actual application was another one. During manufacturing, now you have a sharp corner which caused a crack in this application. What is a lesson learned here is that while you may implement some fillet radii in your application to reduce the potential for fatigue crack growth or fatigue crack initiation, it's important to understand that you may intend something for the drawing, but manufacturing is something else. And so it's important to really inspect and ensure that your part, which may be fatigue critical, be compared against the drawing and ensuring that you haven't violated any of the drawing requirements. Otherwise, you may have unintended consequences, and you may have thought that your design was adequate, but it was not. Here's an example of a jackhammer component showing no signs of yielding before fracture. And in this component, it's quite surprising, but yes, you could get fatigue, and the fatigue could occur with no signs of yielding. So that's very important consideration. You have here a Porsche timing pulley, and in this case, a crack initiated at a fillet. It's a 928 Porsche. You have the bicycle crank spider arm, and you see here a clean fracture, which appears to be a clean fracture. But this particular fatigue crack in a high quality component did take a long time to nucleate from a machining mark. And there, Was not necessarily a stress concentration, but a machining mark, and it was highly stressed at the surface. However, once initiation occurred, it was quite rapid, and it accelerated, um, and you will see these beach marks that we'll be talking about later on. And then you have the ductile failure or the sudden failure in the remaining net section. For some fatigue crack growth examples can occur in tooth failures, crankshafts, and they're all going to have very similar types of beach marks, which I'll be discussing soon. You have here, why don't you take a moment and see why you think, where you think the crack initiated. And I know that I talked about beach marks. Excuse me. But I want to point out that sometimes it's not apparent. In this example, a crack initiated at this stress concentrations, propagated, and they had a final brittle failure here at the very end. You also have fatigue failures that have occurred, initiated in mismatched grease holes. So here you have the whole crack initiates from the sharp corners and then propagates until you have brittle failure at the very end. You also have fatigue failure of a forged connecting rod. The crack initiated at a flash line of the forging at the left edge of the picture. And you can see some of the marks here. And the beach marks are these marks, show crack propagation halfway around the hole before ultimate fracture. And this is your ultimate fracture right here. I think you're suddenly starting to understand how this works. Here's a fatigue failure of a 200 millimeter diameter piston rod of an alloy steel steam hammer loaded axially, and the crack initiated at a forging flake internal to the part. So not always a crack initiates from the external surface, but it can initiate from the internal to the part. And the internal crack grew outward and symmetrically, as you can see. Here you have an aluminum alloy landing gear torque arm assembly, and which required a redesign to eliminate fatigue fracture at the lubrication hole. And so again, fatigue fracture can occur in these types of stress concentrations. And in this case, I ask you to feel free to pause the video and see if you can see signs of the crack initiation and the growth and what could have been the growth failure. So fatigue fracture examples are not new. They're not from the 1900s. In May 8th, 1842, we had the Versailles train crash. The axle of a locomotive train suddenly failed, and it was departing at a birthday celebration of a king celebration, and it caused a derailment, which resulted in a crash and fire, and more than 75 people died in this incident. During subsequent debates regarding this accident, the term fatigue was coined to really describe the sudden fracture of a component from repeated stresses which appeared to be performing well up to that point. So there's no signs of failure until it happened. Now you have the axle here. We know that the axle has to take the weight of the train, and also we know it's rotating. So the axle failed more at a fillet area. And so here you have some sort of rotating beam bending type behavior because the beam is rotating. And so you have bending going on. And so then you had the unfortunate situation where the fatigue crack initiated and propagated. And here's the picture of the cross section. The beach marks are going outwards to the inboard, the hole of the circular cross section, and then you have this ductile failure or brittle failure, depending upon the material. This reference can be found from railway structures integrity past, present, and future. The Comet G ALYY crashed April 1954. Pressure tests had revealed fatigue. And one of the issues is that they were using square windows. And so that was one reason why we had to go oval. There's also, you had the situation of thickening the skin, and so that's one of the things that had to be done. The state's top bridge engineer had to be put on the spot. There's a bridge failure, and there's a significant failure that's reported in the Star Tribune, and fatigue was one of the phenomena that causes failure. So enough about examples. Let's look at some stages of failure, fatigue failure. Stage one is the initiation of a microcrack due to cyclic plastic deformation. It doesn't always have to be cyclic plastic deformation. Stage two is one that progresses from a macro crack and repeatedly opens and closes, creating bands called these beach marks. And then as the crack has propagated far enough, that remaining material is insufficient to carry the load, and it fails by simply ultimate fracture or ultimate failure. And so you can see here the three phases, stage 1, 2, and 3, although here it's called A, B, and C. Here is an example of the features of fatigue fracture surface. Here you have the origin, and then you're going to have different areas of texture as you move along, but you can see here these marks, okay? And then suddenly you're going to have some sort of shear lip that could occur, and that's indicative that now you have turned into a sudden failure of some sort. So region A, which is right here, all in white, we're going to call that the fatigue crack growth area. Over here, the shaded area is a final static failure, or the ductile failure, or the brittle failure that occurred suddenly. And I want to point out a few things. So in these regions where it's not shaded, these regions, the crack tends to be slow. And then you're going to have regions where the crack growth tends to be faster. That's what causes these beach marks in the first place. So what are the fatigue stages for crack growth? And so if this is the loading direction, we will have the stage 1 crack propagation, and the fatigue crack initiation will occur via persistent slip bands. And the small crack propagation will be via a mode 2 mechanism, meaning that the surfaces are sliding relative to each other, regardless of the fact that we're loading in the mode 1 direction. So even though even if the loading is perpendicular to the sample, the crack will start as a mode 2 and then start moving into a longer crack propagation via mode 1 mechanism. Mode 1 here means it opens the crack. Mode 2 means it's sliding. The surfaces are sliding past each other. Here you have a little more details about the initiation process. That's your original surface. You have some amount of intrusion, some amount of extrusion, and then you have the persistent slip bands. We have this stage 1 fatigue crack growth, and you have all these gliding dislocations. But as this occurs and it propagates further, then it will become mode 1. So it starts sliding and then turns into mode 1. And so here you have another view of what we're talking about here. So in this case, You have the loading direction. Again, sliding, and then you're gonna have opening. So again, mode 2 and then mode 1. Locally, the crack grows in shear, macroscopically grows in tension. And then here's an example of what could be happening to the crack tip, as you see. So the fatigue process from the material science perspective is cyclic slip, fatigue crack initiation, stage 1 fatigue crack growth, stage 2 fatigue crack growth, brittle fracture, or ductile rupture, okay? So it's really important to understand that there's these processes that occur microscopically and then turn into macroscopic crack growth, and all of that has to do with persistent slip bands that we talked about. And you're gonna have some surface roughening because of that. Sometimes you get some sort of peeling indication of the surface. So the fracture surface characteristics are important to understand, especially in the failure investigation. You have ductile mode of fracture. The typical surface characteristics will include cup cone, dimples, a dull surface, inclusion at the bottom of the dimple. You could have a mode of fracture that's brittle intergranular, which is between the grains. So that's shiny. The grain boundary is cracking. You may have a brittle transgranular fracture, which is also shiny. You're going to have some cleavage fractures, and it's flat, relatively flat. And then fatigue is going to typically have beach marks, striations, initiation sites. You're going to have a propagation zone and a final fracture zone. So let's focus on this a little bit. I think it's worth looking at, especially if you're working on a failure investigation. This can be very valuable to you. Say you have different fatigue surfaces, and I ask you, hey, where does crack initiate? Where does it propagate? And what does a final rupture look like? So let's focus first on the high nominal stress conditions, which you could have a no stress concentration type, you could have a mild stress concentration, and a severe stress concentration. If you have a no stress concentration type and you have a high nominal stress, in tension loading, for example, then you're going to have an initiation point, and then you're going to have your beach marks, and at the end you're going to have a final fracture. In a milder stress concentration, you're going to have the beach marks are going to look a little bit more different, it's going to look more propagated compared to the first condition, and they're going to have less uniformity. As you can see here, this looks like a set of concentric semicircles or arches. And here you're not going to see that. You're going to start seeing some amount of crack propagation going a little more accelerated towards the edges. Why? Because I have a stress concentration, so it's going to cause the stress to also propagate more towards the edge. And again, this right here, this gap represents that stress concentration. So here's an area that we're looking at, which is right in the center, right there. If I look at a severe stress concentration, you're going to have multiple initiation points, and then and the beach marks will be less. You're going to have less beach marks, and you're going to have a ductile failure or brittle failure. That's for a circular sample. For lower nominal stress situation, notice how you're going to have beach marks that travel more with a final ductile failure. That makes sense because you're giving an opportunity for the fatigue crack growth to occur, right? Here, if I have a higher nominal stress, then it will grow some, but then break suddenly. So that makes sense. If I go with a mild stress concentration, again, this beach mark starts getting pulled downwards because now this stress concentration accelerates the growth towards the periphery of that shaft. And then you're going to have a smaller net section failure area. If I have a severe stress concentration, then it's going to be even more dramatic with beach marks. They're going to look like it initiated here but didn't. It's just that the initiation failure, the initial failure is not as visible, but you still get beach marks until you have a final fracture. So it can get confusing because this one with no stress concentration, high nominal stress to the very left, compared to this one, looks similar because you could confuse this point and these points as initiation points. But the important thing to understand is that this surface is going to look a lot like this one. It could look very rough, shiny. And if you have a stress concentration, it can help you focus your attention and make you understand that perhaps it did initiate towards the edges, but then it propagated to failure at this point. If I look at rectangular samples, it's a very similar situation. Again, no stress concentration, high nominal stress. You'll start seeing some initiation points here. It could look like that. It could look like this. You could have a situation where if you have this type of high nominal stress condition, that the crack could propagate a different location. It could initiate at different points and then leave you with some amount of fracturing left. If you have a severe stress concentration, multiple initiation points possible, and then typically the failure surface will be towards the center, okay? And then I can keep going on. If you have lower stress concentration, more beach marks, more propagation with very little area left for it to fail. And that will be the case here too. A lot of initiation point, multiple initiation points. And then here you're gonna have multiple initiation points, but with final fracture towards the center. So important considerations and if I were to have a keyhole situation, you're looking at stress concentrations now more concentrated towards the keyhole. But in general, again, the same idea, beach marks and then final fracture. And what you don't want to do is confuse the initiation points because it can throw your failure investigation towards some sort of distraction. If you're looking at unidirectional bending, a bending type situation, I'll just focus on these guys, and then I want you to spend some time thinking about the way this looks as here at the bottom. But again, not very different from what I covered on the tensile situation. And if I have reverse bending, then expect two initiation points, one on the top, one on the bottom, if your axis for reverse bending is right here. You can see here that when I go with a lower nominal stress, the beach marks emanate from both ends, and then they cover more area, and then you have this small amount of area left for sudden fracture. With more severe stress concentrations, those beach marks start to look less clean, and you will leave also with a small area. Again, that's for reverse bending. For unidirectional bending, it looks very similar to the pictures I showed earlier. Why don't pause the video and see if this rectangular cross sections make sense to you, as I think you will glean a lot from this. So why this is helpful, again, if you're working on field investigation and you want to back engineer what's going on, then this could be of great value. So another point I want to make is when you're working on rotational bending situations, or torsion as an example. So for torsion, you're going to see for fast fracture, you're going to see a 45-degree fracture condition. If you're going to look at torsion, in some instances, you're going to have a crack that runs perpendicular, and then you're going to have these beach marks showing up. That's for high nominal stress in general. When you move into a situation of a lower nominal stress, you're going to have some cracks going in this direction, but then benchmarks that are emanating from, or they're just forming, and then the center here becomes the final fracture, similar to here, final fracture. And then if you have a very high stress concentration, then you're going to have the benchmarks and then even a smaller area to failure. I hope this makes sense. When you have rotational and bending behavior in those situations, you're going to have less symmetric behavior of those benchmarks, but in essence, it should follow this particular bending situation. But now with the rotational bending, you could start having this propagation in one particular side more than others. And then the final fracture will be towards the end center for stress concentrations that go all around. And here again, with almost no stress concentration, benchmarks that look a lot like the ones we discussed here for pure bending. And then when you add the torsional component or rotational bending, you start getting these non-uniform benchmarks with a final fracture towards the center, but the circles don't look all that uniform and centered compared to a torsion alone. Here's other pictures that are pulled from SAE. So I invite you to kind of pause the video and see if you can determine what is going on with these pictures. And for the ASM handbook, again, more pictures for you to consider and kind of study on your own. I covered all this. And then here, the ASM handbook provides additional pictures for you to study, Figure 49. So fatigue life methods, the methods are required. You require some ways of predicting the number of cycles to failure for a specific level of loading. There's two methods: stress life method, least accurate, particularly for low cycle fatigue application, is the most traditionally used. Strain life method requires a detailed analysis of plastic deformation on these localized regions. You're going to have several idealizations leading to some uncertainties. And low cycle fatigue can be very difficult to predict. I'm going to show you why it's uncertain and why this is such a difficult problem to really predict this accurately. Now, you will be confronted with the situation of having to do it, and my goal is to teach you some of the things you need to consider as you try to use tools for analysis predictions. Now, for like any analysis, whether it's strength, fracture, heat transfer, you need to have some constitutive behavior that allows you to predict what you want to, that allows you to predict the parameters you're looking for. And so here, when you look at fatigue, you really are relying on a lot of test data that allows you to find curves or define curves that you can then use to predict fracture or fatigue. The fatigue methodology typically starts with really understanding the loading history provided, the component geometry, material properties. Once you have that and you have defined the stress strain curves for the materials, then you can go into damage analysis using the service history, the life history, or the service life of the component, with the component geometry, with the material properties. You can then use that information, and then with the fatigue data and those two together, you can determine fatigue life. So fatigue tests typically subject a sample to repeated stress while counting cycles to failure, subject specimen to pure bending, typically with no transverse shear. As a specimen rotates, the stress fluctuates between equal magnitudes of tension and compression, and that we call completely reverse stress cycling. That's one approach, but you could do it for different types of stress reversals. So maybe you test a 100 megapascal on one end, but maybe less, like minus 30 megapascal in the other end. If I go from minus 100 megapascal to minus 100 megapascal to 100 megapascal, I call that fully reversed. Usually the specimens are carefully machined and polished in this type of testing. In 1860s, August showed repeated stresses in railroad axles causing damage. So as a consequence, the rotating beam feature was a good solution to this problem. It imposed fully reversed bending stresses over the entire periphery of the specimen. And the point I want to make here is that Waller sought to define a stress level. He was trying to figure out what stress level will give me infinite life. That's what he was looking for. He was looking if I apply stress amplitudes, is there a stress where I can get infinite life? Is there a way I can keep going forever? And he defined that the endurance limit. So the stress, he found that the stress range happened to be more important than the stress magnitude. The stress magnitude, yes, was important, but that stress range was even more important. So that was a very surprise. And so going to this diagram, you have a applied torque, and then you have this specimen here, which has a spring attached. Well, the spring attached is is causing bending, as you can see. If I have a load P, the moment arm is P times A, so that's the moment right here. But since the specimen is rotating, you're getting a fully reversed bending stress as the specimen rotates. And then you're also getting the cycles in. And so if you have a notch sample, it will decrease the strength, the fatigue curve. So this is stress amplitude versus cycles to failure. And then if it's smooth, then he got this data. Now notice that there's scatter in this data. That's one of the things we're going to see is that even though your specimens are carefully machined and polished, it can still give you scatter in the data. So the Morse test is another type of test that was considered. Sorry about that. And the surface is polished again in the axial direction. A constant bending load is applied. So basically you have this motor, you have this load applied that causes bending to the sample, and then this motor causes rotation of the sample, causing this fully reversed bending stress. So this is one of the approaches that's used, and this is your standard geometry for this kind of test. So what are the effects of diameter on the specimen? If I have a situation where I have a large material, like a large cross-section compared to a smaller cross-section, and it was a hollow tube, then you have a lot of area under a lot of stress compared to this situation. So it was found that even though, I may have this same amount of stress, for a larger sample, it was found that it can reduce the endurance limit because there's more likelihood of microstructural defects being present when you have a larger area. So there were some size effects being found, and so if I had a 0.3-inch diameter, the sample took longer to fail, even though it had a thinner section, but it had the same stress. When I went to a larger diameter, the endurance limit dropped. And what I mean with endurance limit, again, is when I got that infinite life situation. I'm trying to find this line here. So when the stress amplitude reaches certain threshold, below that value, I don't seem to see fatigue. And so that is the point I want to make, is that it was found that for smaller diameter samples, I was impacted less than if I went to larger samples, particularly because the stress was acting over larger areas. So you have a larger possibility of microstructural defects in the sample. Sorry about that. And so what are the types of repetitive loading you may see In general, you may see types of moderate, mild periods, severe periods. But in a ship, you're going to see some weather conditions that can be like a storm. In a commercial aircraft, you're looking at turbulence. But you're going to have a fatigue spectra as a point. In a launch vehicle, you're going to see a different fatigue spectra. But the idea is, how do I count the cycles? How do I count these amplitudes that could be causing a problem for me? And so I want to define right now a little bit some terminology that's going to be useful. So you have, sorry about that, you're going to have the amplitude of that stress, okay? So we're going to call that sigma max minus sigma min divided by 2. We call this a range, sigma max minus sigma min. And then I'm going to have the mean stress, which is sigma max plus sigma min divided by 2. Okay, so that'll give me the sigma max plus sigma min divided by 2. And then one cycle is considered when I return back to that mean value. And then I have R, the R ratio is the minimum peak divided by the maximum peak. So that's another important thing to consider. When do I get a one reversal? When I go from positive, or I'm going from one end to another, we call that a reversal. But for me to have a full cycle, I need to kind of go from one value, and then to a full cycle will represent this one right here. This will be half cycle. And this is an example of a constant amplitude stress history. This is more of a variable amplitude stress history. So again, you could have situations where you have a lot of vibratory stress, but you could approximate that, and we could generally call that a general fluctuating load. A repeated load is one where the loading conditions are being repeated. This is more general because the mean value is arbitrary, so that depends on application. That's sigma max. Okay, if you recall, we call this sigma A, which is sigma max, the sigma max minus sigma min divided by 2. While this dash line becomes sigma max plus sigma min divided by 2. That gives you this dash line. And the range is sigma max minus sigma min. Important to understand all this terminology. And then in this case, I have a completely reverse situation because I went positive and negative, positive and negative, and the mean stress is 0. So reversed, fully reversed is a mean of 0. This one reversal, but in this case, it's not fully reversed, as I had discussed in this slide. So some terminology to consider. Again, the fluctuating stress can be characterized by simply specifying the maximum and minimum stress, and then the mid-range stress or mean stress is important, and the alternating stress component sigma A is the alternating stress component. So that's the one that measures from the mean to the max. Okay, very important to understand this terminology as we'll be using it. So the stress ratio tends to be very important because that tells me if I have a reversible type situation. If R equals -1, then sigma min is the negative of sigma max, which means I have a R of -1, and so I have a fully reversible cycle. Let's look this again here. Sigma max is 300, sigma min is -300. 300 divided by -300 is -1. And as you can see, R -1 becomes a stress ratio that gives me a fully reversed situation. There's another terminology that people use, it's called the amplitude ratio, which is this range divided by the mean. So that's useful to know because it kind of gives you a relative understanding of how much I'm really fatiguing in terms of stress relative to the mean stress. If the mean stress is very high, then that gives you some information about, hey, how much I'm ranging this max to min. How big is that range that I'm talking about here? So this is very important to really understand what's going on. I know I have a lot of information here. I want to cover a little bit about what does R ratios mean in terms of the loading situation. So for R less than -1, you have a compressive mean stress. So that means my mean stress is over here, and then my cyclic behavior is going to look something like this, where I have a lower absolute value of mean stress compared to the max stress. When R is -1, you have equal value of max and min stress in terms of magnitude, and my mean stress is right at 0. So that's fully reversible loading. And then I have a situation where I have a low tensile mean load stress. So the mean stress is about here. And so that's between -1 and 0. And in general, again, this max amplitude, the amplitude of this value, max stress, divided by the absolute value of the mean stress, this ratio will fall somewhere between -1 and 0. Here, the mean stress is slightly larger, but not much larger. And then I have this situation of R equals 0, which means that if I put R equals 0, that means sigma mean is 0. And so that means I have a maximum stress, but no, the minimum stress is 0. And so the mean stress is greater than 0 in this case. A situation like this that we could consider is an aircraft that takes off. An aircraft that takes off and lands, the differential pressure across the skin should always remain positive, but it will increase as I take off because I have internal pressure in that skin to account for the altitude conditions of having almost no pressure outside the cabin. So again, you pressurize the cabin, outside of the cabin, lower pressure, and so that differential pressure is causing this maximum stress. But when I land back to ground, I have a situation where the outside atmosphere is equilibrated with the inside atmosphere. So I have this situation. I don't have the reverse of that, where I have a vacuum type situation. So then another situation is where sigma min and sigma max are both positive, which means that, and it will be a situation where R is less than 1, greater than 0. Your mean stress is much greater than 0 in this scenario. And if R equals 1, that means that sigma min equals sigma max, and you have a constant load, basically probably no fatigue damage there occurring, maybe creep. If R is almost going to infinity, then again, if this is going to infinity, sigma max is going to be 0, and sigma min will take some value, okay? And then this will be the reverse situation as this one, and then this situation will be reversed from that one. This one is considered cyclic compression loading all the time. So loading patterns may be complex, so it's very necessary to simplify it. Small fluctuations may have very negligible effects compared to large cycles. In this video tutorial, at the bottom of this link, I'm going to provide a link to another video that shows how to do this kind of simplifications. Although I'll cover a little bit, but not a lot, not in this video lecture. So when I look at A here, I have this loading situation where this stress is fluctuating, okay, to some level. And you can see this has been plotted here. Now, one could consider this particular increase and drop is not significant to the fatigue life, potentially. You could say that probably about this little peak here. So one approach is to perhaps just go ahead and truncate that and simplify what you really consider a cycle. And so not all cycles really lead to fatigue damage. And so what I'm showing here is something called a Rainflow count procedure. And it helps you identify when any two adjacent reversals in the stress history satisfies this relationship. Now, what I'm going to do, like I said before, this is an algorithm to figure out what should be included, what should not be included, and how to count. Because if I have stress at different levels, I want to know how many cycles do I really have of each. I have the range. I need to have the range in one axis, the mean in another axis, and then figure out, okay, how many cycles do I have of any of this? And which ones do I really need to consider? So again, you have to look at two adjacent reversals in the stress history and then determine whether you should count the cycle. And so I encourage you to look at the link below to study how to do a Rainflow cycle count. I won't do it in this particular lecture, but I'll cover a little bit on how this works so that it's understood. So sorry about that again. As you can see here, this one right here, this Rainflow count can be counted as a cycle because that corresponds to the largest range that I have from this point to this point. And so that one really counts. Then the next one that's big is the one that goes from here to here. So that counts. And then I have the smaller triangles that should be counted. But I don't want to start counting. I want to start counting from the big ones to the small ones. And that's really the way you want to go about it. And the Rainflow counter cycle is identified using when any two adjacent reversals in the stress history satisfy this relationship. That's really when you count the cycle for that. So again, I'll put a link below where you can study other examples. It's going to be a nice video on that. And it's not for me. The SN diagram is really the data that's going to inform for you the life of a part, especially for high cycle fatigue. Also, low cycle fatigue can work as well. The number of cycles of failure is usually plotted in a log-log diagram. So that's typically the way to do it. In this case, it's done log on this axis, and on this axis you have a log diagram as well. For steel, a knee usually occurs about 10 to the 6 cycles, and the strength that corresponds to that knee, we usually call that the endurance limit, or SE. So here in this case, 50 could be considered, 50 KSI could be considered that. And so I'll call this low cycle fatigue typically. There's a small knee here, and then from here on you have high cycle fatigue. Typically low cycle fatigue goes to up to 1,000 cycles. But again, this is not perfect here, because anytime you see this transition occurring, there's a knee there, and then you go into high cycle fatigue, and then from here to here, we hope to have infinite life, but it may not always be the case. This right here is the ultimate stress or strength for one cycle, and we call this the fatigue strength, SF. The SN diagram from non-ferrous materials will typically look like this. For rod, a little bit higher. Again, here you have the peak alternating bending stress, and here in the x-axis, I have the number of cycles of failure. So here, alternating bending stress, and then this one is the life cycles of failure. And so the fatigue strength is typically reported as a specific number of cycles, and permanent mold cast will be lower, and sand cast even lower. And you can see here that at very low stresses, you still have finite life. So the endurance limit is usually presented in a log-log plot with the actual SN line usually representing the mean of the data. Certain materials, primarily BCC steels, have an endurance or fatigue limit, SE, which is a stress below, we believe the material will have infinite life. For engineering purposes, we could consider infinite life to be 1 million cycles, but I will warn you against that, because some applications such as turbo machinery could reach 1 million cycles fairly easily. The endurance limit is due to the interstitial elements, such as carbon or nitrogen in iron, which has pin dislocations. So this prevents a slip mechanism that leads to the formation of microcracks. But this is important to understand that this endurance limit can quickly disappear. If you have overloads, it will unpin these dislocations. If you have corrosive environments, this endurance limit is gone. High temperatures will make it easier to mobilize these dislocations. So it's important to understand that you could have a situation where you thought you have endurance limit, but that endurance limit is gone. Keep in mind that wear can be another situation. Say you have a complex assembly with a relative movement, and that results in localized wear. You could have a situation where the initial surface condition has been worn out to the point that it could start affecting the ability of even retaining this characteristic of endurance limit. So another point I want to make is that if you look at the steel situation, and let's look at this y-axis here is a stress range. And stress range, if you recall, again, you're going to see ascent curves in many different ways. You're going to see alternating stress, you can see stress range, but it's important that you have the right data, you're comparing to the right stuff. Here is stress range compared to cycles to failure. And so if you look at a situation where there's a periodic overstrain, look at how the endurance limit is gone, where I do start having this finite life. If I have an initial overstrain and I do strain control, you're going to have a situation where, for the most part, you have endurance limit, but at 10 to the 70, you start losing it. And so, again, if you have periodic strain issues, there could be a situation where this no longer applies, the endurance limit situation. The endurance limit for steels has been experimentally found and is related to the ultimate strength for most situations. And you will see here some data. In the y-axis, you see the endurance limit. In the x-axis, you see the tensile strength. And so there is a relationship where you can see here that the endurance limit is correlated with the tensile strength for carbon materials, wrought irons, and alloy steels. But in general, you could use this data to kind of guide you through. Not having the data, you could try to make some assumptions that could be of help. So that is what I want to point out here. So if you look at the upper limit, you're looking at 0.6, the lower limit closer to 0.4, but you have a lot of extra data out here. And then on average, 0.5. That ratio of SE divided by SU, the tensile strength. So here's some information that could be useful from a rotating beam specimen. SE prime is 0.5 SUT, and then 100 KSI for ultimate strength, tensile strength greater than 200 KSI. So basically what we're doing is at this point, you draw a line and you say, okay, just use 100 to kind of be conservative. And then this is in a different unit system, but bottom line, this is the approach that people use for steel in general. For cast iron, you're looking at 0.4, 0.4 situation up to 400 or so, and then after that, just keep it constant at 24. So not taking advantage of that full amount. Aluminum alloys, you're looking at 0.4 also, and about 48, just keep it at 19. And then for copper alloys, the same thing. Other alloys are provided here. It's always good to have the test data, but not having it you can still use some of these data. So magnesium alloys, you're looking at 0.35 SU. Copper alloys between 0.25 and 0.5, a big range there. And then aluminum alloys, steels, and irons. You can see additional data given here. For aluminum and copper alloys, there's typically no endurance limit. And so a lot of people think there is, but there's not. Eventually, these materials will fail due to repeated loading. To come up with an equivalent endurance limit, designers typically use the value of fatigue strength at 10 to the 8 cycles to kind of go for a robust design. So we already covered this. So there is a situation here, and there is an influence of the loading on the endurance limit. Fatigue data based on fully reversed rotational bending test show that you get a different behavior. For a bending situation, for bending test, you get a little more benign behavior. If you go axial, you get a little bit worsened the condition. And then when you go to torsion, you get a lot more hit. And so it's important to understand that depending upon your situation, the endurance limit can change depending upon the loading. So if you go to a steels, I had said 0.5, but that's for bending. When I have torsion now, I can drop to 0.29. So it's important to get this right because a lot of people will make mistakes here. Another consideration is that the strength at about 1,000 cycles will be about 90% of the ultimate here for bending, 75% for axial, and then 72% for torsion. So very important to understand that the loading condition can affect the situation at hand. And so a lot of people use the SN curve blindly without realizing what they're really doing. Notice here how the relative stress amplitude is SA divided by SU. Okay, so here we're looking at the stress amplitude now. Important consideration here, as I told you that these SN curves, the y-axis could mean different things at certain times. It depends how the data is collected and how that's transferred into in a SN curve. So for materials exhibiting a knee at 10 to the 6 cycles, you usually have that infinite life. Materials that don't exhibit that knee, then you want to take a finite life if you can, 5, 10 to the 8. Notice that when I use this prime, and I use a prime, the fatigue strength of the specimen is of the specimen. But when I have SF without the prime, that's fatigue strength of the actual component. So something very important to distinguish in the way I'm covering these topics. So graphs can typically be used to estimate fatigue strength if the material and the number cycle is known. There are a couple of problems here. The SN curve sometimes is difficult to obtain and it's sometimes more scarce than the stress strain information. The SN diagram created is usually created in the lab environment for smooth, circular, and it contains ideal conditions. Therefore, analytical methods have been used to estimate the fatigue strength and the endurance limit. Let me discuss infinite life versus finite life. Infinite life implies that it will never break at that endurance limit. And that's the lowest value of strength where that happens. Finite life implies that we know the value of n, that we can find what that is, knowing what the stress range is. And typically, the value will be higher than the endurance. Going back to the prime versus non-prime, I think it's important to understand that the strength variable with this apostrophe implies that the value of strength applies to a lab specimen in controlled environments. A variable without a prime implies that the value of strength applies to an actual case. So SE usually needs to be modified for differences between the lab specimen and the actual condition, and SE depends on whether you consider infinite life or finite life, the value of SE. So again, very important consideration. So if I know SE from a carefully prepared test specimen, and I know this value, I want to find SE for the actual part. I need to make sure I account for the Marin factors. Because testing of the actual part is not practical. So the Marin factors allow me to adjust for this value. A lot of people don't even do this, but it's important. Ka is called the surface condition modification factor. It depends on that surface condition. B is a size modification factor, as we discussed before. Different sizes, larger sizes can affect your endurance limit. C is a load modification factor, so your test may have been done one way, but when you translate it to this AC value for your application, you may have to modify that. KD is the temperature modification factor. K is a reliability factor if you want to account for reliability estimates, because I told you the AC prime is typically the mean value. And then KF can be miscellaneous values. But note, the AC prime is usually a rotary beam test specimen. And SE here becomes the endurance limit at the critical location of the part in the geometry and the condition of use. So again, very two different values. Don't get confused this one with that one. And don't go running with the value from the test specimen. Try to make sure you consider the Marin factors. So the surface finish, KA will consider the surface finishes, whether it's ground, machine, cold drawn, additive manufactured, KBRA covered. KC is basically bending, axial torsion corrections. There's not always a KD here for temperature, but sometimes there is. If you're looking at reliability of 50%, just use KE of 1. And then miscellaneous effects, we'll consider other stuff like corrosion and stuff like that. But that's hard. You have to basically test stuff with corrosion to figure out what the knockdown factor is. So as an example, here is the surface factor case. Stresses tend to be high at the surface. The surface finish has a high impact on the initiation of cracks at localized stress concentrations. The surface factor is a function of ultimate strength. Higher strengths are more sensitive to rough surfaces, so it's important to consider that in your assessments. Here you have 4 different types: a ground one, a machine or cold drawn, a hot rolled, and an as forged condition. And then this is the various exponents and the ultimate strength provided in megapascals in KSI. These will be substituted here, and then you'll find a value of Ka. Some books will have a value of Ka depending upon what kinds of RMS surface conditions we're talking about. As an example from Shigley's book, directly from that, if I have a minimum ultimate strength of 520 megapascals and a machine surface, what Ka should I use? Well, from this table 6.2, I have this condition, I have these values, so I plug it in and get a 0.86 factor. So the size factor is important. I discussed this before. Larger parts have a greater surface area at higher stress levels. Likelihood of crack initiation is higher. Size factor is obtained from experimental data with wide scatter. For bending and torsional loads, the trend of the size factor has been found to be following this stuff. This only applies for round rotating diameter. For axial load, there's no size effect, so we'll just take KB equals 1. But if you have a round rotating diameter, then you have to sort of consider these calculations here. Now, we could verify a value of D that's greater will result in a KB that's lower. So again, important consideration. By the way, these two values are in inches. These values are millimeters. So these two are equivalent. It's just that you have this basically given to you and scaled for the different types of unit systems. Okay. So there's no question that D goes up, KB goes down. And notice that people have found a discrepancy below 2 inches and above 2 inches. For parts that are not round and rotating, an equivalent round rotating diameter has to be obtained. One way to do that is to equate the volume of the material stress above 95% of the maximum stress to the same volume in the rotating beam specimen. So the lengths will cancel, but you want to equate the areas. So for a rotating round section, the 95% area is the area of the ring. And so you have to calculate the area of the ring and then come up with an equivalent value of D for a rotating diameter. And that's given here as an example. That's for the ring and that's for a rotating diameter. And then you solve for D. If you have a rectangular cross section, then again, you equate the area at 95% to for the one of the rotating beam. Here's other size factor calculations, whether it's a square or a circle, I-beam, and so forth. And feel free to pause the video and take note of this. So the question here is, a steel shaft is, and this is from Shigley again, a steel shaft is loaded in bending at 32 millimeters in diameter, abutting a filleted shoulder 38 millimeters in diameter. The shaft diameter has a mean ultimate tensile strength of 690 megapascal, and they want us to estimate the Marin size factor in a rotating mode and non-rotating mode. So I can quickly use the equation since it's a shaft. I can quickly use the calculation, and it's given millimeters, so use the equation I provided, and straight in you get a KB of 0.858. For non-rotating mode, I'll then use 0.37 times D. I get 11.84 and I plug it in and I get a KB of 0.954. So again, I want to make sure I consider the correction for non-rotating situations. So these are for non-rotating. All these DEs are for non-rotating. The loading factor, if you had bending, the value is 1, for axial 0.85, and for torsion 0.59. So you have to correct it depending upon the situation that you have. The KD factor is a temperature factor, and this is specific to steel, but it may change for another material. The point is here that as you go higher in temperature, you're going to affect the KD value significantly. So it's important to consider that that's important to keep in mind in correcting your endurance limits. And here is a formula for it. You can use either this or the interpolation curves. But if you were to plot this, you can get this curve fit and then use that. And here's yet another example. If you have a steel at 70 KSI and it's used, and it's going to see 450 degrees F, quickly plug it in and get a KD of almost has no effect basically. So then for your actual application at 450 degrees F, the endurance limit is mildly affected. And then that's just using interpolation, but you will get the same value as this approach should be. Now, if this is room temperature endurance limit by test. If you only consider tensile strength at room temperature, then you have to multiply it by, you're gonna have to find the value here. So that's interpolated. That's 1.007, which is the same thing I got with this formula. And the tensile strength at 450 can be estimated because it's given to you from data handbooks, and that's 70.5 KSI. And so then you want to then calculate for this particular steel, since you have the ultimate strength and you don't have the value of SE from the coupon, you multiply by 0.5 to then get the 35.2. But this is a better estimate because we got the measurement SE prime directly from the testing. While here, I only knew the tensile strength. Here, I knew SE prime, so I can directly use it. This was a little more conservative. So SE prime equals 0.5. SUT is typical, but represents 50% reliability. It does not imply overall reliability is an important aspect here. So at 50%, K is 1, and 90%, K is 0.8, and then so forth. So K needs to be calculated using this reliability table. So there are other miscellaneous effects like residual stresses, cold working, hardening, corrosion, cyclic frequency, and so forth. So what are the mean stress effects? That is very important to consider, which situation is worse for what. So we want to study that. So here you have a situation where the mean stress is less, then here's fully reversible, and then here is not fully reversible, but SM is greater than 0, okay? And so the stress amplitude in all these cases is the same. Sigma maximum and sigma min is the same. And so it's apples to apples. So if I have a mean stress as less, this slope is going to be better, and your endurance limit will be higher. But if we have everything is in tension, including mean stress, then this slope will look steeper, plus the endurance limit is lower. So as you can see here, mean stress effects do play a significant role. Possibly majority of your tests may be done at fully reversible. And so now, as you can see, the R ratio, which is sigma min divided by sigma max, becomes important. And again, SM equals 0 is R equals -1. And so then it becomes important to understand the effects on the various testing that exist. We could study. So let's look at the alternating stress in the right figure. For constant alternating stress, you're going to see here that for a mean stress that's in tension, the number of cycles to failure is less. When I go to fully reversible, a little bit more number of cycles, and when I go with a mean stress that's in compression, then I get even a higher number of cycles. So the effects of mean stress are quite significant and need to be considered in many situations. On the left-hand side, we see the SN curve for unnotched aluminum alloy bar, but here the plots are given in terms of maximum stress. And so again, like I said before, a lot of test data in the literature is given to you many different ways. In this case, it's given to you in terms of maximum stress and fatigue life with the R ratios provided in this plot. So no wonder it becomes a little more messy to think about it because we've been thinking about it in this manner. But it's important to understand what the behavior looks like here. And so in general, if I have a maximum stress, say it's 50, this particular curve here is R -1. So the R-1 with that particular stress is going to give me a lower fatigue life, okay? But remember that max stress with the R-1 means that the minimum stress is equal to the maximum stress. So the range is actually kind of twice of this 50. So that's 100. And so that's why you have to be careful here on how you use this particular graph, because this is in terms of maximum stress. So a second situation is a maximum stress of 50, but R of 0. Then I have more number of cycles. Why? Because at 50, the max stress is 50, but the minimum stress is 0. So that range is 50. So it's half than what I considered here, right? So here, I have a range that's different from this situation. And that's why I get the higher number of cycles. So again, be careful how you use these plots. Don't pay attention to the labels and try to understand what is going on. But what this is telling us is the greater alternating stress, you get impacted in the number of cycles of failure, but R and that mean stress comes into play and is fairly important. I want to point out that when you go to ultra cycle fatigue, giga number of cycles, it's potential that even though you thought you have infinite life, you could start having some amount of fatigue failures. And so that's something that people have seen, that crack initiation and propagation can occur after a large number of cycles. So you cannot completely discount the fact that that could happen in gigacycles. And again, this is the SN curve to remind you what that looks like. So you can do these calculations graphically, is one approach. You can write the equation for the SN line that goes from 10 to the 3 to 10 to the 6th. And then from here is constant after 10 to the 6th. That's one approach. And the equations of this line are basically fatigue strength equals A number of cycles to this exponent. And A can be approximated as FSUT squared divided by SE. And then this same ratio here without the squared goes in this B here. So with very limited information, you can actually construct the SN diagram for a particular material. As long as you can figure out what SE is, and then this F is typically taken as 0.9, but not always. It depends what the value is at 1,000 cycles. So at 1,000 cycles, you know, it could be a fraction of ultimate strength. So for steel and iron, F is 0.9. And so then you can construct quickly these exponents, and these curves can quickly fall out. For aluminum copper, 0.9 also. And then here's an example, like if you have a rotating beam with an endurance limit of 10 to the 6 cycles, the endurance strength of a polished rotating beam corresponds to 10 to the 4 cycles to failure. And then the expected life of polished rotating beam under completely reversed stress is 55 KSI. So we want to estimate the expected life, the endurance strength, and then the rotating beam endurance limit at 10 to the 6. So we can do that quickly. I know the ultimate tensile strength of this material. So times 0.5 gives me the endurance limit for a rotating beam. And then looking at the literature, you're going to find that F is about 0.86 at 1,000 cycles or so. And so you can use these calculations to plug this in here, and then you get an A of 133. the exponent follows very similar. It's just basically same ratio without the square, and you get a B of 0.0785. So once you have this equation, for 10 to the 4 cycles to failure, plug it in here, and then you get the fatigue strength or the endurance strength. Sorry, the expected life. Okay. I'm sorry, I'm confused. I'm talking about the endurance strength. Okay. And so once I have that, I can figure out how many cycles to failure based on taking this equation here. Using this equation here. So here, that's endurance strength due to 10 to the 4 cycles. And then I have, for fully reversible, 55 KSI, plug it into this equation for which I found A and B exponent, and I get 7.75 10 to the 4 cycles. So these are only estimates, and recall that this is not going to be 100% accurate because of course, the difficulties with predicting cycle life and the scatter you may get in the test data. So if you have another situation is, I have a hot rolled bar that has been machined to a diameter of 1 inch. It is to be placed in a reverse axial loading for 70,000 cycles to failure in an operating environment of 550 degrees F. Using ASTM minimum properties and a reliability of 99%, estimate the endurance limit and fatigue strength at 70,000 cycles. So the ultimate strength of this material is 50 KSI at 70 F for a hot rolled steel bar, which has been machined. Since we're looking at a rotating beam specimen endurance limit and is not known at room temperature, we'll have to estimate it. So we'll first determine the ultimate strength at the elevated temperature first, and you can basically interpolate it to figure it out. And you get that this ratio is 0.979. And so knowing that information and knowing that it's 50 or 70 F, you can then determine that the ultimate strength at 550 degrees is 49 KSI. So it's not a big impact due to this temperature. The rotating beam specimen endurance limit will then be estimated assuming that it's basically half of this ultimate strength. So that's 24.5 KSI for endurance limit in the specimen configuration. So then we have to use the Marin factors for machine surface, and then we get a value of 49 to these values here. 0.963 is a Ka. Since it is an axial loading condition, the size factor is 1. And for the axial loading condition, the size factor in this case is 1, and the load factor becomes 0.85, as we had discussed before. The KD is already accounted for, so you can make it 1, so no issue there. For 99% reliability, use a K of 0.814, and we have no other thing to consider, so then see how quickly this 49 drops. 49 times 0.5 is 24. Sorry, how this 24 drops? You have 24 times 0.963, 0.85, 0.814. Now it dropped all the way to 16. So consider that it took a big drop. So we need to construct the SN equation. We use a F of 0.9 again. And then I can plug it into this equation here. SC is 16.3. F is 0.9. Tensile strength is 49. So A is that value. B, the same thing as this, but without the square. And then a third with the log, minus 0.1441. And so finally, for the fatigue strength at 70,000 cycles, we're looking at HCF equals 23.9. So that is a fatigue strength at that value. So I hope this example is clear, and you can see how the marine factors, if not accounted for, can lead you astray. And you can make a mistake if it's not considered. So how to go ahead and account for mean stresses? So we talked about fully reversible, but if I want to figure out where's the infinite boundary, infinite life boundary, where should I be designed to get that infinite life? We could use something called the Goodman or modified Goodman diagram. And so the way this works, you plot the endurance limit and the ultimate strength, and you draw a line. And then you can also draw the Langer line, that's from the yield strength to the yield strength. And then on the x-axis, you have the mid-range stress, and the y-axis, you have the alternating stress. And the idea is to stay in this zone here. I'll put another link to video that my brother created that goes into that, so you can see how that's done. But here is a quick reference for you to follow. So here is another view of that. You can plot the mid-range ratio, mean stress divided by ultimate strength, and mean stress divided by ultimate compression strength. And then you have the amplitude ratio of SA divided by the endurance limit, the theoretical value, or from the specimen design, that's why there's a prime. And you can see that there's very little effect in the mid-range value when you go negative. And all the data has been normalized in this manner to kind of show you the trends. But again, very limited impact in the performance when you go into compression. So there is a lot of different failure criteria to demonstrate infinite life. One is, for example, this yield line is called. You have the Goodman line. You have the Soderberg line, which connects SE and SY instead of SE and SUT. That's a little more conservative. You also have the Gerber line, which does a fairly good job of that. So again, these lines are intended to give you a prediction of when you get infinite life. And as you can, if you stay here in this zone here, you're fairly safe. But it is fairly tough to come up with the right one for every situation. And again, the safe zone is not showing up here, but this is your safe zone typically. And this, again, draw the yield curve, yield to yield. These are alternate stress. These are mean stress. And then draw the line from here to here. And that gives you the endurance to the ultimate. And then this becomes your safe zone where you have potential infinite life. But again, this value becomes extremely important to get, and it's important that we consider the marine factors. Otherwise, you're going to be way off. Other commonly used failure criteria are given here. I plotted the SAME elliptical line and many other lines. So just keep in mind. So for design, you can just stay in this zone here, shown here. The modified Goodman is linear and is more conservative than Gerber, is an observation. And Soderberg provides a very conservative single check of both fatigue and yielding, so not a bad line to use. It's fairly conservative. The Langer line represents a standard yield check. So that's, one, but then you're operating above the endurance here. And here are some common equations, but now showing the factor of safety. So if you want to apply a factor of safety on infinite life, typically 1.25, you put it here and then draw the lines accordingly. And here, this helps out figure out the number of cycles to failure when you have fluctuating loads. These are mean stress, the alternating stress, and then the ultimate stress, ultimate strength. And then the A and B are found through experimental data, this beta and so forth. I'll give you an example later. This is a summary of some of the equations you may see and how to find a factor of safety. And this is how the different coordinates intersect. but I think it's fairly simple to draw it graphically. Here, the same way it is for the Gerber equation in this column. Here is where the coordinates are intersecting, and then the factor of safety, the calculation for that. And the ASME elliptic, for this course, we'll probably focus on the Goodman part. Let's look at this example. It's an interesting example from the Fundamentals of Metal Fatigue book, straight from there. Say you have a component that undergoes a cyclic stress with a maximum value of 110 ksi and a minimum value of 10 ksi. The component is made of steel with an ultimate strength of 150 ksi, an endurance limit of about 60 ksi, and a fully reversed stress at 1,000 cycles of 110 ksi. So they're asking us, using the Goodman relationship, determine the life of the component. So fairly difficult problem because we're combining multiple concepts here now. And so we want to tackle the problem little by little. And so here's the stress amplitude. We discussed this before. Sigma max is 110. Sigma min is a 10 divided by 2 gives me 50. The sigma mean is 110 plus 10 divided by 2 is 60. So now we want to generate the diagrams as we discussed before. And so we can then look at this equation here, sigma A. We'll just use a Goodman line to figure it out, is basically what we're going to do. So let me go straight to where we want to go. So the first step is the alternating stress in our condition, if I go back, is 50 ksi. And so the alternating stress is 50 ksi. The mean stress is 60 ksi. So draw the alternating stress in the y axis, and the x-axis draw the mean stress. So here, this point corresponds to 50 and 60. Draw your ultimate strength point here, and then draw a line towards your endurance limit of 60 ksi. So that's this line right here. And so that's really what you want to do. The problem that we have here is that the point, the operating stress, did not fall within this region here. This region here will have been safe, but since the point lies outside of this line that connects the endurance limit at 60 ksi, remember that's the 60 there, and the ultimate value is 150. So this point is that point is that, this point is falling outside. So I draw a dashed line to figure out where it intersects the alternating stress. That's 83. And so I have to figure out, now I have finite life because of that. And so my question is, if I have finite life, how many cycles of failure do I get? So you draw a line all the way to 83. That's the approach you want to use. That's what you will get is 83. So 50 divided by this SA plus 60 divided by 150 is 1. So this gives you 83. Now go to your SN diagram. The SN diagram at 1,000 cycles is 110 KSI. They tell you that per testing. And then here at 60 KSI is your endurance limit. Okay. And that's usually at 1,000,000 cycles. So you can draw this line very readily. Go here, say, okay, I have 83 KSI. And then this tells me that I'll have 2.4 10 to the fourth number of cycles. So that's the solution to this problem. Again, in summary, calculate alternating stress, the mean stress, plot that into the Goodman diagram. This point falls outside. Then figure out, okay, draw a point from here to here, but extrapolate all the way to alternating stress to figure out what that value is. Plug it back into an alternating stress here in this plot, and then calculate the life. Now, this formula will work very similar to this formula. They do very similar things. Sigma A is given, sigma M is given, sigma ultimate is given. So you can then determine the number of cycles of failure using that formula as well. So let's look at example number 2. A steel bar undergoes cyclic loading such that sigma max is 60 KSI, sigma minimum is minus 20 KSI. For this material, the ultimate tensile strength is 80 KSI, the yield is 65 KSI. And then the fully corrected, it's already been corrected for the Marin factors. The endurance limit for that is 40 KSI with an F of 0.9. We want to estimate the number of cycles to failure using the modified Goodman criterion. I won't do the Gerber criterion. I will flash it for you. You can pause it and then study that on your own. The alternating stress then becomes 60 minus 20 divided by 2, that's 40 KSI. The mean stress becomes 20 KSI. Notice how that's a positive value. And then this could be a quiz question is, if this is a smaller mean stress but with the same amplitude, which one takes more cycles to fail? I'll let you think about that. So we want to use this criterion. And now for the modified Goodman criteria, the fatigue factor safety based on infinite life is using this formula here. So we put it in here. So 1 divided by sigma alternating is 40. The endurance is given to you as 40. The mean stress is found as 20. And then the ultimate tensile strength is 80. So you plug it all in and you get 0.8. That's a factor of safety less than 1. So clearly, we are predicting a finite life now. So the SN diagram is only applicable for completely reverse cycles is the problem. So to estimate the finite life for fluctuating stresses, we will have to obtain an equivalent completely reverse stress that is expected to be damaging as a fluctuating stress. So a commonly used approach is to use the modified Goodman diagram. So that it represents all stress situations. And so again, you will generate a line that passes through this point like we did before and this point. So there's a high diagram between this point and that point. And then you find the alternate stress based on that. You extrapolate. The point where this line intersects this alternating stress represents the completely reverse cycle, the equivalent value. And that equivalent value is sigma m equals 0. So you can use that to figure out what is that. And that point is going to be 53.3, okay? When you figure out where it intersects. So since it's 53, you can use that later. We're going to use that later. The first step is to find A and B. So A, F is 0.9, SUT is 80, endurance is 40, calculate A, calculate B. Again, this stuff without the 2, log 1/3. And then you have this value is 53 from this equation. And so from there, the number of cycles gives us 30,000 cycles. And so that is the finite. And so you get 3.4 10 to the 4th cycle. Sorry about that. So what do you do with cumulative fatigue damage? A common situation is that you have a stress level with the n number of cycles. And say you did the rain cycle counting we talked about before, which you're going to watch a video at the bottom of this link. And then you have a stress with n number of cycles and so forth. So say you have 50 KSI stress range, but that's about 20,000 cycles. And then you keep going on and you have different distributions of stress and number of cycles, as shown here. So it's been shown that Miner's rule is one approach that people have used. It has is a linear damage model. It was developed in 1920s to 1945. It has shortcomings, but it's commonly used to be able to come up with an equivalent behavior for what the damage is. And so it was used in bearings, and it was later modified for aircraft applications later. And so what is the idea? What is the idea that we're trying to do. So the idea here is that you want to figure out the number of cycles to failure to that stress range. That's the first step. But you know the number of cycles applied to that stress range. And so then you can then take all these ratios and sum them up. And the idea is that you want this total damage to be less than 1 if you can. That's a general approach. And so experimentally, it was found that when testing was done, this value D actually came out more between 0.7 and 2.2, but on average, it was about 1. So again, there are some difficulties here that decreases your confidence because you wonder, what value is going to hit. So one approach that people do is they make sure that you apply a factor of safety on this damage, and that factor typically tends to be 4. And to illustrate Minor's rule, all you're trying to really do is you're trying to determine, after you apply the stress at that many number of cycles, you want to figure out what is the new fatigue curve. That's really what you're doing with these calculations. I'm illustrating what this formula does, but it's not necessary for me to cover this because you can just use this formula to figure it out. Generally speaking, I think what is important is that verbally, what I want to explain is that when you consume 60 KSI, 3,000 cycles, you consume some amount of life there. And when you do that, you're going to naturally reduce this curve into this dash curve as a consequence. Okay, and so what's going on? So at 60 KSI, I run 3,000 cycles. So 60 KSI, the question is how many cycles to failure? So I go 60, hit this line, which comes from test data, and then I go down here and say, okay, that's 8,500 cycles or so. So that's what comes out here. So if I use Minor's rule, I can figure out how many cycles I have remaining for this problem. So then I have N2, which is 3,000 cycles, N2, which is 8,500 cycles. I can solve for N2, assuming that N2 is 10 to the 6 cycles, because I want to figure out how this point gets impacted. And when I do that, I get an N2 of 6,480 cycles. That corresponds a line all the way up to here. So you can then draw that point, okay? And so the idea here is you're trying to determine that knockdown factor due to consuming some of that life. Again, you don't have to do this. We can use this approach very readily to figure out the cumulative damage, but this is just another approach into trying to figure out what is happening physically. And then here again, 8,500 cycles, and then you consume 3,000 cycles. What is the impact to that? And so that tells you how much it drops and how much this line moves because of that. Again, every time you consume life, this line drops more and more and more. So that's the idea of illustrating Minor's rule. But Minor's rule is not very accurate always. Manson rules Minor's rule does not account for the order in which stresses are applied, but Manson rules does. It overcomes those deficiencies. But it requires that each line be constructed in the same order in which the stresses occur, and that's not very easy to do. So rarely used, but please look at this and consider the Manson's method as a potential method to really account for the order of stresses in which things occur. Typical data for scatter factor. There's a lot of scatter factor in this kind of testing. SN data usually include only a few data points at various stress levels. Fatigue cracking and nucleation constitutes the majority of the fatigue life and is highly dependent upon the surface finish and quality. I told you that those samples are tested very carefully, but you do get a significant amount of scatter in the data. And you can see here, if I divide by 4, if I take the median and divide it by 4, I start to envelope more and more of that SN diagram, this SN data here. This comes straight from this book, Fatigue Life Scatter Factors in Aircraft Applications. There's a NASA NESC video that I think you should look at from the Academy. I've had you look at some of those. It will go into some of this. The northern scatter factor of 4 only really applies in a linear regime of the SN curve. The variance is large at number of cycles above 10 to the 5. You can see that here, the variance is quite significant. And 10 to the 5, you can see the variance taking off. In other words, you could be quite off predicting fatigue life at those high values. And that's why applying a factor safety or scatter factor on your predictions is recommended. Even a factor of 10 is even better. The typical scatter factors do not really apply to very low cycle fatigue because the data is more tight. I'm going to go ahead and say that, go to here, the scatter factors here. Based on some aerospace standards, a scatter factor force applied to the service life. So you can apply it directly to the cumulative damage index is one approach. A D of 1 is usually failure, and you can accept it to 0.25, a damage of 0.25. So if you can keep the cumulative damage less than 0.25, you're in better shape. For high cycle fatigue, as I discussed, a 10x factor is recommended. You can see here that any error can have orders of magnitude difference, and that's why that will protect you right there for that. Here's some pictures that I found from online sources. There's a turbo machinery. You can see that stress concentrations can be obtained from closed-end solutions. You know that, we just cover that. And in the homework, you'll be doing plenty of that. The alternate stress and mean stress can be determined from finite element models. And the finite element models should have the sufficient fidelity to capture the response at fitted locations or geometric features that produce a stress concentration. The point I want to make is that stress concentrations do affect fatigue life quite significantly. And so it's important to understand that those need to be well characterized in your models. So given a stress concentration, you want to look at calculating KT. KT is the peak divided by the average stress across this part. And so, or it will be sigma peak divided by S, the far field stress. That's your peaking factor or your stress concentration factor. And so you're going to obtain a stress concentration factor, and this is called the notch sensitivity. So the idea is that a stress concentration factor is going to have a notch sensitivity, and we want to find out the fatigue stress concentration factor due to that notch. And I think this becomes very important. You can see here a notch radius is going to have different notch sensitivities. The bigger the notch radius, the notch sensitivity is less. So if you approach 1, then Kf becomes Kt, and there's no that's what you get. But for very small notch radius, you start getting a Q closer to 0, which means that Kf becomes 1. And I'll explain what Kf is basically your fatigue stress concentration factor. For shear, you also have a very similar formula. These are the equations if you didn't want to use the curves, but we'll skip that. And for most cast irons, Q equals 0.2 is a good value. Kf, the way you use this, Kf is a multiplier to increase the nominal stress. That's really what it is. So designers, instead of using Kt and increasing the nominal stress, use Kf and increase the nominal stress. Designers sometimes apply a 1 over Kf as the Marin factor to reduce AC. That's one approach. For infinite light, either method is fine, since of course this is equal to that. I mean, you can put the KF above and you get the same thing. So for finite life, increasing stress is more conservative. Decreasing the SC, the endurance life, applies more to high cycle than low cycle. But it is important to consider, and this is the Collins method to derive this fatigue life curve. You basically want to knock it down by sigma ultimate divided by twice KF. Here, this endurance limit for steel, so that's why that sigma ultimate divided by 2.5 times sigma ultimate, and then you further knock it down by KF. Here's an example on how to deal with it. I'll welcome you to pause the video and don't look at the solution. And then if you got it right, then congratulations. Very simple problem. Here, all you're trying to do is calculate given a steel shaft in bending with the ultimate strength of 690 megapascal and a shoulder with a fillet radius of 3 millimeters, what we want to do is find the KF for this problem. So you can readily find D over D, so that's 38 over 32. The R over D, that's 0.093. And then you can read the graph to get the KT of 1.65. That's looking at these curves right here. Okay. And so once you have that, you can calculate KF, and that's 1.55. And then you can use equations 2 and you get the same answer. Once you get that, you can take the nominal stress from your calculations, increase it by 1.55, and then use that to get your fatigue curve, SN curve. And then you can look at another example of we can look at another example of a rotating shaft simply supported with a non-rotating force of 6.8 kilonewtons. And then you can calculate the maximum moment due to this loading condition. And then just use the Marin factors for bending. In this case, Kc, Kd, Ke, and Kf are equal to 1, so no effects there. But you have that 0.5 that plays a role. The surface factor does play a role, and then the size factor plays a role. But other than that, you have reduced the AC prime, you reduce it all the way to AC after applying the Marin factors. And you drop from 345 to 236. When you have multiple combinations of loading, things get a little more complex. But a formula like that could work out. You can get sigma A prime, the alternating stress, the mean stress using these formulas, which will include the fatigue stress concentration factors. So here's yet another example on how to deal with it. I've shown this before, and then you have to basically use the Rainflow cycle count to reduce the data. And this what is repeating. And what you want to do is determine failure. So that's the example given here. And again, the ultimate strength here is 152. So F is usually 0.9, but here is 0.795. S is 67.5. We found it. That's not related to this example. So that's a different example. And then you can now calculate the fatigue. You can now calculate number of cycles of failure based on that. And then here, Gerber fatigue criterion was used, but we won't be using that in this class. We'll be using the Goodman diagram the most. Okay, I'll go ahead and skip these examples and I'll go to low cycle fatigue. Low cycle fatigue occurs in situations where you have high plastic deformation. Let me first explain monotonic stress strain curves. So I have a stress strain curve that looks like this. I load it up, and then I plastically deform it. And when I unload it, I get some plastic deformation. So the total strain is elastic plus plastic, as you can see here. When I have cyclic stress strain curve, I have the situation where the stress increases, you unload, and then you have a hysteresis loop where now the stress range becomes all the way from here to here. So you have reversed that stress, and then as a consequence, you also have reversed a strain. All this is elastic, this portion, and this whole thing is plastic. So here's your whole strain range for cyclic stress strain type of behavior. Again, monotonic, apply the loading, unload. But here you're going cyclic, and so you go tension, and then you compress the sample, and you're following this curve now. And then you bring it back in tension, and then you continue to collect the data. What people have found, and Manson Coffin both independently formulated this in the 1950s and 40s, is that it does follow some sort of relationship. And these plots, you need to be careful. Some of these plots can be the total strain range, or it could be the plastic portion of the strain range. But bottom line, this is found empirically. And again, you're going to see here low number of cycles to failure. With very high strains, you can have very low cycles to failure. So it can be curve fit again. Again, all this stuff is curve fit. You need test data to figure it out. So a strain life method is usually approached for this kind of problems, and you can use it. You can use the Miner's rule as well, no problem. But it's important to understand that we typically use the strain life relationship when we expect low cycle fatigue. And again, we're talking about the normal low cycle fatigue range, which will range between 100 cycles to somewhere in the range of 5,000 cycles. It depends when the knee starts occurring, as we had discussed. The low cycle fatigue characteristics is such that the cyclic behavior is more in the plastic range, much more significantly than high cycle fatigue. The stress strain cycles that cause low cycle fatigue cracking are produced by significant levels in loads. You see microscopic changes in the materials, dislocations, and then some quite plastic deformation occurring. The low cycle fatigue tends to be highly statistical in nature too. You have a lot of scatter in the data. You get moderate deformation. You can get a fracture dependent behavior depending upon time and temperature. So low cycle fatigue does depend on that. Thermomechanical fatigue becomes important when you have thermally induced stresses, and the fracture surfaces can also be affected by oxidation and alloy depletion. Here's some of the apparatus really used in the gathering some of this data. You have it for tension compression with a notch and then with a hole. And the strain hardening behavior is also found and that becomes important when you're doing these calculations. Under cyclic loading, materials can actually harden, soften, or be stable, or be mixed. For soft materials, the initial dislocation density is low. The plastic cyclic behavior increases the dislocation intensity or density. So here you have a situation in A where you have a constant strain amplitude. The stress response here is increasing over time, and this is your cyclic stress strain response, okay? So this we call cyclic hardening in this situation. Notice how 0.135, how as the number of cycles progress, this stress is increasing. We call this cyclic hardening. For hard materials, cycling can rearrange dislocation. So these for soft materials, these for hard materials. And it offers less resistance to deformation. In these scenarios, you may see a situation where for constant strain amplitude, the stress decreases. And you can see that here as well. the stress is decreasing over time. We call this cyclic softening. We also have the situation of, we can see all that now. So you have hardens, then softens, and then softens. So annealed will behave this way, partially annealed this way, and cold work this way. The strain life method, basically, fatigue failure almost always occurs at a local discontinuity. When stress at a discontinuity exceeds the elastic limit, plastic strain will occur, like I discussed. The cyclic plastic strain can change the elastic limit, leading to fatigue. So it's true stress strain curve for the hysteresis. You want to do a modeling that accounts at least for 5 reversals to really understand that strain range that it should be included in strain life methods. And so there's different approaches. You have the total stress range, the total strain range, depending upon how the data comes to you. You have the plastic strain range and the elastic strain range. And so that data needs to be considered, depending upon what data you have, then you have to properly select it from your models. The relation of fatigue life to strain, here you have an example of a strain amplitude given to you and reversals to failure given to you. So again, different data provided. You also have the fatigue ductility exponent is the slope of the plastic strain line. And you have the fatigue strength exponent is the slope of the elastic strain line. And again, so you have this exponent and then you have this exponent. This one is for the plastic portion, this is for the elastic portion. And these two fatigue exponents really drive the behavior of the strain to failure calculations. So the total strain amplitude, if you're to do it in terms of total strain amplitude, the number of cycles to failures can be calculated using this formula. And here the total strain to amplitude considers both the plastic and elastic. And B becomes the fatigue exponents, which are provided to you. Parameters for fatigue, this is another way to look at this same formula here, but here, and then shown to you in terms of the stress strain curve. So you can look at it all in one place. But I'll go to the bottom line here. The Manson-Coffin equation is a great equation to use. People use this all the time. You can correct it for mean stress using this equation here. Okay, so the mean stress goes here, the ultimate stress goes here, and then this formula tends to do very well for mean stress calculations. And then please read these 2 papers here at the bottom. Pause the video, download the papers, and read them. And then the Maurer equation is given here. And the Smith-Watson-Topper equation is given here. You will have a homework that goes through all this. But for now, please have a good day, and I'll talk to you later. Until the next lecture, and stay safe.